What specific problem does LookAhead Tuning aim to solve? And what are the critical challenges in preserving model security during fine-tuning that the paper addresses?
LookAhead Tuning aims to solve the problem of safety degradation in large language models during the fine-tuning process, particularly when enhancing their capabilities with domain-specific data. The critical challenges in preserving model security that the paper addresses include the neglect of the impact of benign data on model safety, limited methodological adaptability, and high computational demands. The paper emphasizes that even benign training data can lead to catastrophic degradation of protective mechanisms, necessitating a method that allows models to acquire new capabilities while maintaining their safety. LookAhead Tuning proposes a solution by modifying training data to preview answer prefix tokens, thereby reducing loss associated with these tokens and minimizing disturbances to the model's initial outputs. This approach effectively balances the dual objectives of improving task performance and preserving safety mechanisms.
How does the proposed LookAhead Tuning method work? Illustrate the implementation of both the real answer and virtual answer approaches step by step.
The proposed LookAhead Tuning method works by modifying the training data to incorporate initial tokens of the answer, thereby enhancing the model's safety during fine-tuning. 1. Real answer approach. For each training instance, I_I, O_I, the first M tokens of the ground truth answer, O_I lec M are appended to the input instruction, I_I, using string concatenation denoted as I_I O plus O_I lec M. This modification encourages the model to generate the initial tokens accurately, reducing the loss associated with these tokens and minimizing perturbations in the model's output, thus preserving safety. 2. Virtual answer approach. Instead of revealing the actual answer's prefix, this approach incorporates a generic prefix, P-E-G, let's solve this problem, into the response. For each training instance, I_I, O_I, the input instruction is modified to include this prefix, ensuring that the real answer remains unrevealed while still guiding the model to generate safe outputs. Both methods aim to balance the enhancement of domain-specific performance with the preservation of safety mechanisms in large language models.
Can you provide a simple yet illustrative example of how the real answer approach modifies the training data? Walk through the key steps involved in this approach.
The real answer approach modifies the training data by directly incorporating the initial tokens of the ground truth answer into the input instruction. For each training instance, I_I, O_I, the first M tokens of the ground truth answer, O_I lec M are appended to the input instruction, I_I, using string concatenation denoted as I_I O plus O_I lec M. This modification encourages the model to generate the initial tokens of the answer more accurately, thereby reducing the loss associated with these tokens. By focusing on the initial output tokens, this approach minimizes perturbations in the model's response, effectively preserving its inherent safety capabilities. Overall, this method ensures that the model retains its safety mechanisms while being fine-tuned for specific tasks.
What are the practical benefits of using LookAhead Tuning compared to traditional fine-tuning methods? Discuss improvements in safety and performance based on the evaluation metrics used in the paper.
LookAhead Tuning offers significant practical benefits over traditional fine-tuning methods by effectively balancing safety and performance. The proposed methods, real answer and virtual answer, enhance safety by previewing the initial tokens of the answers, which mitigates the risks of safety degradation during fine-tuning. Evaluation metrics indicate that LookAhead Tuning, real, achieves the second-best performance in terms of raw safe rate, RSR, and utility across datasets, while LookAhead Tuning, virtual, attains state-of-the-art performance, ranking first across all metrics. Additionally, both methods require only a slight increase in computational time, 1. 65% for the real variant and 2. 56% for the virtual variant, demonstrating their resource efficiency. Overall, these results highlight that LookAhead Tuning not only preserves model safety, but also enhances downstream task performance compared to traditional methods.
How was LookAhead Tuning validated or tested? Describe the experimental setup, datasets, and metrics used to assess the effectiveness of the proposed methods in maintaining safety and improving task performance.
LookAhead tuning was validated by fine-tuning the Llama 2-7B chat model on the GSM-8K and Samsung datasets, which were selected for utility and safety evaluation. The experimental setup involved comparing the proposed methods against several baselines, including the seed model, vanilla fine-tuning, FT, SDFT, and constrained SFT. For the real answer approach, the number of previewed tokens was set to m equals 6, while the virtual answer approach used a buffer prefix of "let's solve this problem." Effectiveness was assessed using accuracy for the GSM-8K dataset and Rouge 1 for the Samsung dataset to measure utility, alongside safety evaluations using raw safe rate (RSR) and jailbreak safe rate (JSR) with the HEX-Phi dataset. The results indicated that LookAhead tuning methods outperformed baselines in both safety and task performance metrics, demonstrating their effectiveness in maintaining model safety while enhancing performance.
What specific results did the authors report regarding the performance of LookAhead tuning in terms of safety and utility? How do these results compare to traditional baseline models? And what limitations does the paper acknowledge about the proposed approaches?
The authors reported that LookAhead tuning, both real and virtual approaches, outperformed traditional baseline models in terms of safety and utility. Specifically, LookAhead tuning real achieved the second-best performance across datasets for raw safe rate (RSR) and utility metrics, while LookAhead tuning virtual attained state-of-the-art performance, ranking first across all metrics evaluated. In comparison to baseline methods, the proposed approaches demonstrated significant improvements in maintaining model safety while enhancing task performance. However, the paper acknowledges a limitation regarding the trade-off between safety and downstream task performance. Increasing the number of previewed tokens enhances safety but can negatively impact the model's performance on tasks. Additionally, the authors note that the real variant is more suitable for low-resource scenarios, where exposing the initial tokens is acceptable, while the virtual variant is designed to protect these tokens better, albeit with slightly increased resource consumption.